Okay, what we're going to do today is talk about power. You guys have done a power tutorial and a little power lab. I just wanted to give you this little kind of online lecture to make sure that you guys are understanding everything that you need to know so far. What I'd like you to do is take notes on your own paper while you're doing this, and then you'll just turn in those notes as a PDF as your homework today. So when you talk about energy, one of the weird things we've done is we've talked about amounts of energy and changes in systems. For example, we talk about, let's say a car starts at position A and its speed is 0, and at position B its speed is, 10 meters per second. And if you know the mass of the car, then you can figure out something about the energy change from A to B. So, in your notes you should maybe pause right now and consider a system where we're talking about the car and the air, and the car on the earth and the air surrounding it, and sketch a little energy bar graph. And I'll just wait here while you do that. Okay, I'm tired of waiting. Hopefully you just paused the movie. So at the beginning, like let's say this is a real car. Zoom, zoom. At the beginning, the car's got, gas in its tank. And so the energy stored in the system might be stored as chemical energy. You might have imagined that it was a wind-up car, in which case you might have elastic energy. Or you might have imagined it was a battery-powered car, like a toy car, in which case you'd probably still have chemical energy at the beginning. And then in our system here, there's no energy transferring in or out of the system, but at the end you know that that chemical energy has changed into a different account, and it's probably in the kinetic energy account. Okay? And some of you might have put some thermal energy in there. Maybe have one less kinetic energy, one more thermal energy, and that's okay. But for now, let's just pretend that the thermal energy increase is very small, that the increase in temperature in the system is very small, so we don't need to worry about it. But we've got to change from chemical energy to kinetic energy, and that happens when the car, this 5 kilograms, accelerates from 0 to 10 meters per second. But what that doesn't take into account is how much time does it take, right? In other words, if you have a car that accelerates very slowly or a car that accelerates very quickly, is there a difference in these bar graphs? The example that we had on the online tutorial was one where you ran up some stairs, right? So if I start at the bottom of the stairs carrying a snack, at A, my EG is 0, and at B, my EG is bigger than 0. And so again, let's pause for a second. And if I walk up the stairs, or if I run up the stairs, is my change in the gravitational energy bigger when I walk, or bigger when I run? When is the change in EG greater? Okay. So if you pause for a little bit and answer that question. Okay. Then, hopefully, you've thought about this and you think, well, if EG is just m times g times h, well, that's the same number whether I run or I walk. And then, again, it seems kind of weird because your changing gravitational energy is the same, but there's got to be something that we can talk about that takes into account the fact that we're doing it faster. Okay. So let's imagine what that faster might look like. Oops. Let's not. Can we add a page? I don't know. We'll just add a page. Oh, there we go. Button. Let's imagine now a graph of the gravitational energy in the system versus the time. And this will be in seconds. This will be in joules. And so let's say I run up the stairs at a constant speed. Then that graph might look like this. Okay? So let's say this is walking. So right now, take a guess. If I run up the stairs, what will the graph look like? Hopefully, you imagine a graph that looks like this. And hey, hopefully, the more savvy of you guys know, if you run up the stairs, the amount of the energy changes the same. And so here's what we got, right? This is the same number. You change from 0 at the bottom of the stairs to the same number at the top of the stairs. And what's really different is how much time it took to do it, right? So if we run, can I do this? Oh, look at that. If we run, the slope of the graph is steeper. And so we're going to focus on that slope. What does the slope of any graph tell you? Okay, what does the slope of any graph tell you? Hopefully you're thinking, slope tells me the rate of change. Right? The slope of any graph, the rate of change in y with respect to the x. So, what's the slope of this graph? This slope is the rate of change in what? With respect to what? And hopefully you guys know. The slope of this graph is the rate of change in the energy with respect to the time. You can put EG if you want to, because that's the energy that's changing. Doesn't matter what energy is changing, but it's the change in whatever energy you're looking at versus the time. And that is the definition of power. Okay? So the big thing that you have to understand, power, is the rate of change in energy. With respect to time. Or, how do you find power? You find the slope of the graph of energy versus time. Power is the slope of an energy versus time graph. Right? So mathematically, what is this energy, what does the power equation look like? If it's the slope of this graph, take a look up here. We got energy, we got time. How would I calculate that? That's right. It's change in energy divided by the change in the time. Now, if power is change in energy over the change in time, what are the units? Okay? Well, change in energy is in joules, change in time is in seconds. So the units of power is a joule per second. And a joule per second, if you've done the tutorial, you'll know, is a what? A joule per second is a what? A what? Yes. A joule per second is a watt. Okay? So 1 watt is a joule per second. Now let's do a, is there a practice problem here? Yes, there is. Let's do a practice problem. A 60 kilogram box is lifted straight upward by a rope, a distance of 10 meters at a constant speed. How much power is required to complete the task in 5 seconds? So first let's draw the situation. Got a box, 60 kilogram box. We're going to pull it up. It's going to go up 10 meters. Right, so this is my mass. This is my distance, or I'll call it my height. And it takes 10 seconds. Okay, so let's think about this as an energy problem. If you have the earth in this box as your system, and let's say not the rope. Okay, so the earth in the box, but not the rope. What's our energy bar graph going to look like? Hopefully you understand if you're at the ZRL and we're moving at a constant speed, then we've got a kinetic energy here, and we'll also have a kinetic energy here. That's the same. But the gravitational energy will increase between A and B, sorry. The gravitational energy will increase. And how does that increase? It increases because there is work done on the system. So this is a little arrow that does some work. So now you think, well, energy is changing. How can I figure out the power? Power is change in energy over change in time. Okay? So let's look at our givens. We're given mass is 60 kilograms. Height is 10 meters. Delta T is 10 seconds. Okay. Sorry, that should be an equal. There should be a colon. There we go. Now we're trying to find the power. Okay. So power is the rate of change in energy. There are two energies changing here, right? The work and the gravitational energy. Okay. So we could pick either one of these two. But do you guys know how to calculate work? We kind of do, but we haven't done a whole lot of it. But you do know how to calculate the gravitational energy. The work changes from, the work is the energy that changes in the system. You can calculate that certainly by using the force times the distance. Or we can calculate the gravitational energy as a change in energy. So the power equals the change in gravitational energy over delta T. Okay. Hopefully you guys understand what I'm saying. The power here is the same. We can either say it's work over change in time, or it's change in gravitational energy over change in time. Either of those equations is correct. This one is hard for us to figure out. This one we can do. So let's do it. So if the power is a change in gravitational energy with, over time, then we know that the change in the energy, gravitational, is m times g times h. So the power is going to equal m times g times h over change in time. And so now I can just plug in some numbers. My mass is 60 kilograms. My height is, does that say 10 seconds? I'm sorry, I was looking ahead there. I wrote this down wrong. Hopefully you noticed that. The gravitational field strength constant, 10 newtons per kilogram. And the height, which is 10 meters. And we're going to divide that by the time, which is 5 seconds. And that gives me a power of, you take out your calculator, and you say, hey, 60 times 10 times 10 divided by 5, 1,200 joules per second. But that is the same thing as 1,200 watts. Okay, and that's a simple power problem. And interesting thing to know, 1,200 watts, you can write that as 1.2 kilowatts. Right? Kilo is that metric prefix meaning 1,000. So 1,000 watts equals 1 kilowatt. Another weird thing, if you think about units of power, if power is the change in energy over change in time, then you can think about energy as power times the change in time. And if you look at your electric bill, you'll see that they charge you with something, they charge you for energy in a unit called the kilowatt hour. And this equation here is where you can understand what a kilowatt hour is. So if you think of energy as measured in joules, power is measured in watts, time is measured in seconds, then 1 joule is equal to 1 watt second. It's kind of a weird unit, okay? Kind of like a Newton meter is a unit of energy. The energy when you push with a force of 1 Newton over a distance of 1 meter. A joule then is the amount of energy that's expended when you have a 1 watt power output for 1 second of time. But in your house, you use a lot more than single digit watts, right? So your oven, your air conditioning, all the lights in your house, your hair dryers, your microwave oven, they use an insane amount of energy, and so you measure your power in kilowatts, right? So this watts is a power unit, and this seconds is a time unit. So you usually measure your in SI units in a science class, you would measure your power in watts and your time in seconds. But to be more practical in your home, you measure your power in kilowatts, and you measure time in hours. So this would be like if you had, I don't know, 100 watt light bulb, and you had 10 of them. Okay, that would be a kilowatt of power that you're using up. And if you left them on for an hour, then that would be 1 kilowatt hour of energy that's expended by those 10 100-watt light bulbs that are on for an hour. So hey, if we tried to figure out, hey, how many joules is 1 kilowatt hour? Okay, well, we could do a little unit conversion. 1 joule times, now it's time for fractions, right? That is a funny looking time sign though, and a funny looking J. Sorry, I'm sitting on the chair and my arm's kind of caught funny. 1 joule times fraction. Hey, look up here. This is a great thing to know. 1 joule is 1 watt second. So we can put 1 joule on the bottom of this fraction, and we can put 1 watt second on the top of this fraction. And then we move to the next fraction. Joules goes away, and now we're trying to get to kilowatt hours. Well, we know that 1 kilowatt is 1,000 watts. And now watts goes away. And then we can go from seconds to minutes. 1 minute is 60 seconds. And then we can go from minutes to hours. 1 hour is 60 minutes. And so we know that 1 joule is, I'll just hit here, 1 divided by 1,000 divided by 60 divided by 60, 0.0000028 kilowatt hours. Okay, so 1 joule is not a whole lot of energy if you're your electric company. All right, let's go back and do this the other way. Hey, 1 kilowatt hour is how many joules? Okay, so do the unit conversion the other direction. 1 kilowatt hour, and then fraction time. Okay, so we know that if we put kilowatts on the bottom, put watts on the top, we know that 1,000 watts is 1 kilowatt. Kilowatts goes away. And now we're in watt hours. We need to get to watt seconds before we can change to joules. So we'll go from hours to minutes. 60 minutes is 1 hour. From minutes to seconds. 60 seconds is 1 minute. And now, that wonderful fraction that we learned a couple pages ago, 1 watt second is 1 joule. And now seconds goes away. Watts goes way over here. Goes away, and we're left with joules. So now we've got 1 times 1,000 times 60 times 60 equals 360,000 joules. Joules is 1 kilowatt hour. So when you look at your electric bill and you see how many kilowatt hours you're being billed for, you can see that that's 360,000 joules. Okay, well, hopefully these things are a little bit more clear to you now. I'm going to give you single problem homework assignment in addition to this in today's homework, and then you'll send me a PDF of your notes and the homework assignment as your work. Bye.